Okay, good morning. Let's continue with our COMG 302 research methods. Last time, yesterday, we talked about concepts and, mostly variables. So today we'll continue. So it will be our third lecture, and it's the third part on concepts, constructs, and variables. As usual, we'll have a quick review of what we went through last time. So last time we talked about different types of variables. So we have, first of all, if we consider the kind of values that variables can take, we have categorical and continuous variables. So what are some examples of categorical and continuous variables? You should be able to do that for the exam. So let's say, we can easily say, let me call out my pen. So what are some examples of categorical variables? What do you think? So we can say biological sex, that's definitely a categorical variable. What about your religious denomination, right? The religion that you believe in. Or we can say whether or not you are a user of Facebook. User of Facebook. So why is this a categorical variable? Because the answer to this question, are you a user of Facebook, is binary. You either are a user of Facebook or you're not a Facebook, right? It's not continuous. It's not like you can gradually, move from a user of Facebook to some intermediate state of usership and then all of a sudden become a user of Facebook. So your answer will be either yes or no. And these two answers are mutually exclusive. They're non-overlapping, and usually we don't think there's a reasonable intermediate state between yes and no that will make much sense. So we say that this is definitely a categorical variable. Okay. What about continuous variables? Lots of them, right? We said that income is a continuous variable. Age, how about that? Is also a continuous variable. Time definitely is a continuous variable. What else? How about the years that you have spent on social media? Okay, social media. How about that? You can spend 1 year, 2 years, 2.5 years on Twitter, on whatever, right? And all those values can form a continuum, right? Continuum starting with 0, and well, the endpoint really depends on your age, right? And it's really a continuous one. So those are examples of continuous variables, right? Good. Then we talked about, depending on the function of a variable, it can be either a predictor variable or an outcome variable. So, a predictor variable is really something, a variable that predicts, right? We can say x predicts y. Oops. Or x explains y, or y depends on x, y is a function of x. Right, there are many ways to describe this relationship. But regardless how we describe this relationship, as long as it's x that predicts and y is the variable to be explained, to be predicted, y will be the outcome variable. Okay? Pretty straightforward. For example, your GPA predicts, I don't know, how happy you are. Maybe, I don't know. I'm just making things up, right? So, happiness. Okay, you know what this is. So GPA predicts happiness. So in this case, GPA is a variable. It varies from 1.0 to, I don't know what's the highest at here at UH. Let's say it's 4, right? So it will be 1 to 4. So it's sort of a continuum. And then you can ask people, how happy are you? 1, not happy at all, to 7, very happy. So in this case, we're explaining why people are happy using the person's GPA. Okay. Okay, so next we talked about, how we can more precisely describe this relationship, right? First of all, we say that it is very likely, let's continue with this example, right? So we have GPA, and then we have happiness. So we say that very likely it will be a relationship that can be described by a straight line. And because of this, we call this relationship, or we call this correlation, right? A linear relationship, a linear correlation. Okay, it's a straight line. That's why. And following that, we talked about different kinds of linear relationships, different kinds of linear correlations. So first of all, we have positive correlations. This is a positive correlation because this line, you know, um, arranged as such, means that if we, if we move in this direction, right? So okay, where's my pen? Here's my pen. If we move in this direction, right? So that means as your GPA increases, right, from here to here, your happiness will also increase in this direction from here to roughly here. Okay, from here to here. So you see the values of this variable and the values of this variable, they change in the same direction. They increase at the same time, right? So that's why we say this will be a positive correlation. Then how about a negative correlation, right? We say that a negative correlation will be something like GPA happiness, right? Maybe you would say, hang on, that's not necessarily the case. Maybe the higher GPA you have, the more pressure you have, right? The pressure of maintaining that GPA. So because of the high pressure, you will actually feel less happiness. That's possible. But anyway, right? So we say that this line represents a negative correlation because in this case, if we move, in this direction, right? And that means once your GPA increases from here to here, right? your happiness score will drop from this point to this point. So you see, as your GPA increases, your happiness score will decrease. One increases, whereas the other decreases. That means the values of this variable and the value of this variable, they change in opposite directions, right? So this is opposite directions, right? Increasing, decreasing, opposite direction. Increasing, increasing, sorry, increasing, increasing, same direction. So negative correlation, positive correlation. Okay? So let me repeat. When we say a correlation is positive or negative, does not mean this correlation is good or bad, right? It's not negativity or positivity here do not mean valence, right? Rather, it means whether or not the values of the two variables change in the same or change in different directions. Okay? All right. Okay, so this is exactly what I have to say on this slides, right? Positive correlation, relationship, association means the values of two variables change in the same direction. A negative relationship, negative correlation, association means the values of two variables change in opposite directions. So in these scenarios, we'll say X positively or negatively correlates with Y. A typo here, sorry. So there should be Ly here, right? Ly. Positively or negatively correlates with Y. Okay? So these are the definitions of positive and negative correlations. Okay? Good. Alright, so far we have been talking about linear relationships. It turns out that the world that we live in is not that simple, right? The relationship between two variables cannot always be described by a straight line. Sometimes it is described by a curve. And when that happens, we'll have a curvilinear relationship. Right? So if we return to our, formidability hypothesis, right? It is very possible that the correlation between physical strength and proneness to anger is not as simple as the researchers believed. Instead of a straight line, it might be a curve like this. So you can easily see, right, what this curve means. It means that, if we designate that this end means one is weak, here, this end of continuum means the person is strong, right? And this end means a person is very easily prone to anger, whereas this end of continuum means a person is not prone to anger. So we can sort of start to describe what this curved line means. It means, as a person, or as, physical strength increases, right? Because you're moving in this direction. So as physical strength increases, the proneness to anger will, of course, first of all, also increase, right? Imagine a point moving from here to here, let's say. Okay? So as long as we're talking about this half of the sphere, right? It looks very much like a positive correlation, right? As physical strength increases, that person is more prone to anger. But then everything will change after we go beyond this point, right? we can still have our physical strength increase beyond this point, but directly opposite to what's happening here. As we become stronger beyond this point, people will no longer become more prone to anger, right? Instead, they will be less and less prone to anger. All of a sudden, while this half, we're describing a positive correlation, in this half, we're describing a negative correlation, right? Because in this half, as the value of one variable increases, the value of a second variable decreases, right? So that's what I mean, it's not a simplistic straight line linear relationship, rather it changes. Okay. We have a name for it. It's called a concave relationship when a curve is arranged as such. But at the same time, we can have a different type of curvilinear relationship. It's what we call a convex relationship, right? So in this case, everything is the opposite as what we have with a concave relationship, right? So again, we have sort of a division. Oops, it's a little off, but you know what I mean. So there's always also a division, right, between the two halves of this curve. So if we look to the right, to our left here, right? So as a person becomes stronger, that person, up to this point, right? That person actually will be less and less prone to anger. But after this person moves beyond a medium level of strength, right? So this is weak, medium, and very strong, right? As a person moves away from being, of medium levels of strength to very strong, then all of a sudden the person will become more and more prone to anger, right? So again, we have opposite types of correlations, all summarized in one curve line. Okay, so that's why we say this is a curve linear relationship. Okay, so I'll have some text here, to describe these two types of relationship, because I will upload the slides later, and therefore I will not spend too much time here, reading through the text, right? You can easily read them yourselves. Okay, why do I have a box here? I don't know. Okay, so here is another topic. So previously, and please let me have some water. So previously we said that we can have linear and curvilinear relationships between two variables, right? That's really the most simple scenario that we can possibly envision. We call those scenarios bivariate, correlations. So bivariate, right? Bi, V-A-R-I-A-T-E. Bi means two, right? Variate simply means variables. So relationships between two variables. But in actually many, many cases, we can just focus on two variables for reasons that we'll discuss very soon. In many cases, we have three, we have four, and sometimes we can even have hundreds of variables to consider at the same time. So if that happens, what can we do, right? can we still describe the relationships between all those variables? Well, the answer is of course we can, but to do that, we need to understand some concepts. So let's, for the purpose of this class, consider a scenario that has 3 instead of 2 variables. And that will be our upper limit, so to speak, for this class. Because once you understand a third variable situation or a 3 variable situation, you can easily extend the same idea, to situations that have more than 3 variables. So a 3 variable situation is the foundation to understand multivariate relationships. Okay? Alright, so there are 2 situations that we will discuss. The first situation is when the third variable is a confounding variable, or simply a confound. The second situation that involves a third variable is when that third variable is a moderator or a moderating variable. Okay? So depending on what the third variable is, a confound or a moderator, the nature of the relationships will be vastly different. Okay? So let's go through them one by one. So first of all, let's talk about a confound. So let me just first of all give you the definition of a confound or a confounding variable. So this definition essentially tells us how to identify a confound, right? That means when we see a situation that has 3 variables, how do we know that the third variable is a confound? So the first criterion is that the confounding variable must correlate with both the predictor and the outcome variables. So let's start with the 2 variable situation. Here we have variable x, and then we have variable y, and this arrow pointing from x to y means x predicts y, right? We use x to predict or to explain y. Now, we have a third variable then. We add a variable z to the situation. So you might ask, without knowing, what a confound means, you ask, okay, so what does z do here, right? How will z impact the correlation between x and y? Well, it turns out that the first thing we'll examine is whether z correlates with x and correlates with y. So in this case, let's assume that z does correlate with y and, z correlates with both x and y. Okay? So that's why we have arrows pointing from z to x and arrows pointing from z to y. The second criterion of identifying a variable as a confound is when the correlations between the confound and the predictor and outcome variables are statistically controlled for. We'll explain what this means, right? But for now, just, learn this by heart. The original correlation, that is, the correlation between the predictor and outcome variables, will disappear. Once the third variable fulfills all three criteria, we'll call this third variable a confounding variable. Let me repeat, right? If we can establish that first of all, a third variable correlates with both the predictor and outcome variables, and once we can control these two correlations between the confound and predictor, between the confound and outcome variables, right? Two correlations. Once these two correlations are statistically removed, that would be another way to express the same idea. Then the original correlation that existed between the predictor variable and the outcome variable will become zero. When that happens, we'll say that the third variable is a confound. So graphically, it looks like this, right? So we have two variables, x predicting y, and before we're adding z to the scenario, there's a correlation between x and y. It can be negative, it can be positive, it can be linear, it can be curvilinear, doesn't matter, right? So if variable z is a confound, first of all, z must correlate with both x and y, right? And once we statistically control for this correlation and this correlation, the original correlation between x and y, here designated by a solid line, is gone. Now it's designated by a dashed line, meaning the correlation between x and y disappears. And when that happens, we say that the original correlation between x and y is spurious, or spurious, depending on how we pronounce the word. It's, well, spurious, okay? Or it's fake. It's not true. It's not reliable. There are many ways to express the same idea, but that's what a spurious correlation means. A spurious correlation means once a third variable, the effect of the third variable is controlled for, the original correlation is gone. When that happens, that correlation, we call it spurious. Okay? And variable z is a confound, or a confounding variable. Another way to think about it is x and y are related, or appears to be related to each other, simply because a common factor z. Z, the existence of z, is the reason why x and y are related to each other. Once we take out the effect of z, that is, once we statistically control for this correlation and this correlation, there will be no more correlation between x and y. And that's why we call z a confound. It's actually a good thing, right? Confound sounds negative, but it's actually a good thing, because now we discovered the true reason, the true cause of this correlation, right? It's good. It's actually a very valuable very valuable piece of information to have. So let's look at some examples. Some very famous examples that involves confounds. So it turns out that, for example, there is a very strong correlation between a person's size of shoe size, and that person's math skill, how good the person is at math, solving mathematical problems. And this correlation is positive, right? A line is arranged as such. So that means as a person wears larger shoes or bigger shoes, the person will be better at solving mathematical problems. That's correlation. And that correlation does exist. The question is, of course, that doesn't make much sense at all, right? There's very counter this correlation is very counterintuitive. How could a person's shoe size correlate with the person's math ability? So that poses a question for researchers to explain, right? To explain this unreasonable correlation, to explain this correlation that doesn't make much sense. So what's your thought? Why do you think that shoe size would correlate with math skill at all? This correlation does exist, but our job is to figure out why this correlation, which should not exist at all, is actually observed. Another way to phrase this question is there a third variable whose existence cause this fake or spurious correlation to exist? Is there a third variable because of which shoe size and math skill become associated with each other? Okay, I give you a few seconds to consider. And you can pause before I announce the answer. The answer, if you're ready, is age. I think that makes a lot of sense, right? As you become older, you wear larger shoes. As you become older, your brain actually develops better and you'll be better at solving math problems. I bet that now you will be very good at solving math problems that you encountered in the first grade, right? You're better. You become better as you grow older. So that means what really correlates with math skill is actually a person's age. But just so happens that as you grow older, you will also become your feet will also become larger, and as a result, you wear bigger shoes. So that's the reason that we can observe a correlation between shoe size and math skill. The only reason that these two variables, which should not correlate with each other, correlate with each other is because they're both related to a third variable, which is age. Make sense? I hope it does. Well, let's look at another example. Once upon a time, researchers discovered another surprising correlation, and that correlation is between murder rates and the sales of ice cream. They discovered that as in a city, ice cream sold better, murder rates increased. Why would that happen? As if we sell more ice creams, we're producing more murders, more horrible crimes. That doesn't sound very reasonable, and this correlation again is very counterintuitive. It can't be true, right? How would these two variables that are very, very different, well, I shouldn't say that, well, but you know what I mean, right? So these two variables should not be related to each other, and they're not. And now we observe this spurious correlation again because of a certain third variable. This third variable, as in the previous example, must correlate with both murder rates and ice cream. And it should provide a good explanation why these two would appear to be related. Okay, so again, I'll give you a few seconds to consider what could this third variable be. Right? Okay, you can pause, but if you're ready, the third variable, as some of you or all of you might have guessed, is heat. It makes sense because as weather becomes warmer, definitely you will sell more ice cream. But at the same time, it turns out once the weather becomes warmer, people will become more aggressive. And the result of more aggressiveness is increased murder rates. So again, right, ice cream sales related to murder rates simply because both these two variables are related to heat. As weather becomes warmer, you sell more ice cream. As weather becomes warmer, you observe more murder cases. And as a result, it appears that ice cream sales will increase along with murder rates. But again, this correlation is spurious. It's not real, it's fake. It's fake because this correlation exists only because they're both related to the third variable, which is heat in this case. Okay? All right. So let's, repeat our definition for confounding variables. That is, if, the two variables x and y, they have a spurious correlation, that means this correlation between x and y will be gone once the correlation between the confounded x, heat and ice cream sales, for example, and the correlation between confounded y, heat and murder rates, for example, when these two correlations, correlation 1, correlation 2, when these two correlations are statistically controlled for, the original correlation between x and y will disappear. Right? And that's when we call this correlation between x and y is spurious. But the question, of course, is what does it mean to statistically control for a correlation in the context of identifying confounds? Okay? Well, to statistically control for the effect of a confound, variable z, it is to examine, I'll just read this verbatim, the correlation between the original two variables, x and y, at every value or every level of z. I hope this makes sense because z is a variable, right? It's a confounding variable. And we said in the previous lecture that the definition of a variable is it can take different values. Sometimes we'll call those values levels, right? So that's why we say, why this phrase, every value of z should make sense, right? So when we're examining the correlation between x and y at every level or every value of z, if the correlation between x and y still holds, then the xy correlation is real. It's not fake. It's not spurious. However, if the correlation between x and y, when examined at every value of z, is reduced to 0, then the correlation between X and Y is spurious. Okay, this will sound, I'm sure, quite foreign to most of you. That's understandable because it is not some kind of idea that we talk about with our friends at a bar, right? We don't discuss, oh, a correlation is spurious when we're drinking Heineken, but that's exactly why we need this class to introduce to you this very important idea in analyzing data for all kinds of purposes. You can go to marketing, you can go to education, go to PR, you can go to law firm. It is guaranteed that you will encounter some kind of relationship like this, and you should be able to understand the idea behind it. Okay? So this is the definition of statistically controlling for the effect of a confound. That is to examine the original correlation, the correlation to be explained, the correlation that we would like to demonstrate as spurious at every value of z. If at every value of z, the correlation under examination still holds, then the correlation is real. But if the correlation to be examined or under investigation, it's reduced to 0 at certain value of z, then this correlation between X and Y is not real, it's spurious. Let's look at an example. So we'll use this example between, the correlation, spurious correlation between math skill and shoe size as a demonstration. So here we have the two variables, shoe size and math skill, right? And we can plot all the data points. So we use triangle to represent math skill and shoe size, square to represent shoe size. So if we look at these data points, they do appear to be a very strong positive correlation, right? So if we draw a line through this data points, we see a pretty, okay, this is not perfectly straight, but you know what I mean here. It's a linear relationship, right? So now our job is, since we know that this correlation is spurious, we need to explain why it is spurious. And fortunately, we have the tool to our use, and that's the definition that we discussed just now. That is, once we introduce a third variable, age in this case, and once we start to examine the correlation between math skill and shoe size at every level of age, we will see whether this positive correlation will still exist or be gone. Okay? So to do that, we need to introduce the third variable, age, into this graph. Okay, I do have a line here. Anyway. Okay, so what I did here is I rearranged this coordinate so that I keep math skill here, but I replace shoe size with age at the x-axis because our goal is to examine whether at each level of age of 10, age of 20, age of 30, age of 40, age of 50, right? That's at every level or every value of age, whether the correlation between math skill, triangles, and shoe size, yellow squares, whether the correlation between these data points still is positive. Okay? If the correlation between math skill and shoe size at each level of age is still positive, then the correlation between these two guys is real. But if at every level of age, the correlation between shoe size and math skill is gone, then the correlation between math skill and shoe size will be spurious. So to facilitate our examination, I group all those data points roughly at each level of age. We can definitely be more concise or precise, so to speak, but I believe that this crude categorization should suffice our purpose, right? So these data points correspond to the math skill level of math skill and shoe size at age 50. These will be math skill and shoe size at age 40, at age 30, 20, and 10. So roughly, actually, well, if for illustration purposes, right, it turns out that despite that there's overall trend of positive correlation, right? So if we ignore the groupings, if we only focus on the overall trend, it does appear that there's a positive correlation between math skill and shoe size. But once we focus on the correlation between math skill and shoe size at each level of age, all of a sudden the positive correlation is not there anymore. What really happens is a flat line, flat line, flat line, flat line. In other words, there's no real pattern that can best describe math skill and shoe size at each level of age. And previously, if we recall, we say that once we say that the two variables have no correlations, we can use a flat line to represent the zero correlation, right? Here we see we have flat lines between math skill and shoe size at each level of age. That means there's actually no correlation between math skill and shoe size at every value of age. That's what we mean by statistically controlling for or removing the effect of age. And once we do that, the correlation between math skill and shoe size is gone. It's no longer a positive correlation that they appear to show. In actuality, there's no correlation between math skill and shoe size. Okay? So dashed line again represents a spurious correlation. That's when we ignore age. So there's overall trend that appears to be positive, but once we take age into consideration, that is, we examine the correlation between math skill and shoe size at each level of age, it's actually zero correlations, right? Zero correlation, zero correlation, zero correlation, zero correlation. Okay, that's what we mean by identifying confounding correlations. Okay? Alright, so now let's move on to talk about a second scenario that involves a third variable. And also, please let me have some water. Okay. Again, we'll start with the definition of moderator. A moderator, or a moderating variable, is a variable that may or may not correlate with the outcome variable, right? It doesn't matter. It can correlate with the outcome variable, but it doesn't have to. But what is important about moderator is that once we include, or once we consider the effect of moderator, the strength or direction of the existing correlation will change. Let me repeat. A moderator does not have to be related to an outcome variable. It doesn't have to. It can. But what is important about a moderating relationship is once we include or consider the effect of moderator, the strength and direction of the existing correlation would vary. Once that happens, we observe a moderating effect. Okay. So let's use the formidability hypothesis as an example. The hypothesis says stronger individuals are more easily angered. So we say that this hypothesis makes sense, well, to a certain extent. But let me ask you, could there be any sex differences? That is, does this hypothesis hold for men as well as for women? That is, could we possibly observe different kinds of correlation between physical strength and proneness to anger for men and for women? Is this correlation between physical strength and proneness to anger the same or different for the two sexes? Now, of course, we can say they're the same. The correlation does not change at all, regardless whether we consider men or consider women. That's fine. But what is potentially more interesting is this correlation might differ depending on which sex we talk about or which sex we investigate. So there are a number of possibilities. Possibility one is that for men, physical strength very strongly predict, positively so, proneness to anger. So we use 3 pluses to present it's a very, very strong correlation. 3 pluses, right? It is possible that the correlation is still positive for women, but it's relatively weaker, only having 1 pluses. So that's the difference in terms of strength, right? The strength between the original correlation between strength and anger proneness is very strong for men, but less strong for women. So that's possibility one. Okay? So we can also visualize this correlation here, or this type of 3 variable correlation here. So we can, of course, start with a coordinate. We have strength, because that's our predictive variable, and we have anger, right? So originally we'll have just one line if we don't consider any sex differences, right? But now we can't just have one line because we need 2 correlations, one line for each, because now we are considering 2 sexes. So we're going to erase this one line and see how we can represent the 2 correlations on one coordinate, which is very easy. So let's start with man. Well, simply because I talked about man first. So we say that it's a very strong correlation, and usually when we say a correlation is very strong, we will represent this very strong correlation with a steeper line, right? It's the same idea when you say the hill is very steep. This is a steeper line. So that represents a very strong correlation, and we can say, well, this line represents man. Okay, now we have women. Women, there's also a correlation between physical strength and anger proneness for women, but this correlation is less strong, but still positive. So we can have a second line here. we use a dashed line, a less deep line to represent women. So now we have the same coordinate, but two lines representing two correlations, one corresponding to men, or one and the other corresponding to women. And we definitely see that these are two different lines, representing that the correlations between strength and anger differ between men and women. Okay, so that's how we plot a moderation effect. Now, this is only our first possibility. We can have a second possibility and a third possibility. So a second possibility is that whereas the correlation between strength and anger proneness is positive for men, it becomes a negative correlation for women. It's possible. I don't know why, but we're just considering all possibilities here, right? You can also say, well, it could be a negative correlation for men, positive correlation for women. That doesn't matter, right? It will be the same idea. So again, we can consider how we plot this moderation effect, right? So we have strength, and we have anger. Okay, so again, we'll have our first line. Let's get this guy out of the way. We have positive correlation between strength and anger proneness for men. So we have a positive, we just say, well, this is positive correlation. And we say this for man. Okay? And then we have a negative correlation between strength and anger proneness for women. So what do? How do we draw a negative correlation? You're right? It will be a line pointing downward. And we use a dashed line to just, to make it more distinctive from the line for men. Doesn't matter. You can use dashed line for men, solid line for women. Doesn't matter at all. As long as, readers can readily distinguish between these two lines, that will suffice the purpose. So now, very easily, we have a plot for this moderation effect, right? Positive for men, negative for women. All right, possibility 3 is that the correlation between strength and anger proneness is positive for men, but zero. There's no correlation at all between strength and anger proneness for women. Now, how do you plot this correlation? How do you plot this moderation effect? Okay, I'll leave that to you as sort of a exercise. It's not a homework. It will not be graded, but it will be worthwhile to consider this because you bet that there will be similar questions on the exam. Okay. So in all three possibilities, a person's biological sex is the third variable, but in this case, it's not a confound, but a moderator, because it changed in the first scenario, right? In this scenario, it changed the strength from very strong to slightly strong. Therefore, the strength of the original correlation between strength and anger proneness. In these two cases, well, in this case in particular, it changes the direction, right? One is positive, the other is negative correlation. So it changes the direction of the original correlation between anger and strength. In this case, it's both direction and strength, right? A positive versus a zero correlation. This is stronger than this one, and in terms of direction, they're also different, right? So that's why people's sex is a moderator here. Okay, so I hope this makes sense. Okay, so exercise for you guys. I'll give you sentences below, and your job is to identify from the sentence the predictive variable, the outcome variable, and the moderating variable. Income predicts happiness in China, but not in the US. Well, I make this up, right? There's no reason at all why this should be the case. I'm just using sort of an example here, which doesn't have to be true. It can be very well false. Okay, so in this sentence, what is the predictor, what is the outcome variable, and what is the moderating variable? I give you 2 seconds to consider. Okay, time's up. If you're ready, I'll announce the answer. So in this case, income is the predictor, or levels of income, right? It predicts happiness, pretty straightforward. Happiness is the outcome. Then where is the moderator? Is the moderator China? Or is US the moderator? If you answer China or answer US, you're wrong. The moderator does have something to do with China and US, but neither China nor US itself is the moderator. The moderator is country. It's not a game of word. If you think about it, China and US are the values that the country takes. Country is a variable. China is not a variable. It does not change. It will be at the same place, you know, Eastern Asia. U.S. is also not a variable. It'll always be there in the foreseeable future, right? It doesn't change. It's a constant. So China, U.S., they're not variables, but they're values that a country can take. A country can be China, can be U.S., can be the U.K., can be the France. It doesn't matter, right? So the moderator here is country. Country takes the value of China or US here. So how do we plot this moderation effect here? We start with coordinate. So what shall we put here? Income. All right, predictor. Usually at the x-axis. What do we put here? Happiness. Outcome usually is placed at the y-axis. Happiness. Okay. All right. So I didn't specify the direction of the correlation. So let's say income positively predicts happiness in China, but not in the US. All right. So let's say income and happiness is positively correlated with, they're positively correlated with each other in China, but there's no such correlation in the US. There we go. Okay. Easy, huh? Right. Those are just answers. What culture? That's another way to say it. Right? Okay, another exercise. Drinking impairs men's IQ but improves women's IQ. Again, I make this up, right? Don't think this is true. Excessive drinking impairs IQ either way, right? Regardless whether you're a man or woman, I just make this sentence up for the purpose of an exercise. So that's a note. Okay, so what is the predictive variable here, and what is the outcome variable here, and what is the moderator? Again, I'll give you 2 seconds to consider before I announce the answer. Okay, time is up, and the answer is as follows. Predictive variable is drinking, because drinking is what is having an effect on IQ. So outcome is IQ. All right. So what is the moderator? Is the moderator man or is the moderator women? Again, if you answer man or women, you're wrong. The correct answer is biological sex or gender, doesn't matter. So again, man is not a variable here because men are men, women are women, they're not changing at all, right? What is changing in the sentence is their biological sex. In one case, referring men, in the other case, referring women. So men and women are two values that this variable biological sex can take. Just as in the previous example, right? China and the US are the two values that country, the variable, can take. All right, so if that's the case, how do we plot the moderation effect here? Should be very easy, right? So we have a coordinate, so we have drinking. Oops, drinking. Okay, and then we have IQ, right? So drinking impairs men's IQ. That means, if we have too much drink, men's IQ will drop. So increase, decrease, we have a downward shooting line. This is for men. Oops, for men. Okay, there's an M here. For women, drinking improves women's IQ. That is, as drinking increases, IQ will also increase for women. So it's an upward shooting line. Women. Okay, there we go. That's our moderation effect. Okay? All right. One last important point I would like to make regarding correlation, and we'll close this lecture on that point. Oh, okay. One more exercise before I close the lecture. It is also possible that give you a graph like this, and it asks you, based on the graph, identify what is the predictor, what is the outcome, and what is the moderating variable. Okay? So here, I'll give you a few seconds to consider. Okay? Or you can pause. But anyway, whenever you're ready, right, you can pause to think. So instead of wasting more time or seconds and let the file become very large, I will just say the answer. Answer is GPA is predictor, because usually we place the predictor variable at the x-axis and the outcome variable, which is support of gun control here, at the y-axis. The moderating variable here, well, first of all, we are observing a moderation because the correlation between GPA and support of gun control is not the same for COMG students and psychology student. For COMG student, as their GPA increases, they become more supportive of controlling gun. Whereas for psychology student, as their GPA increases, right, they actually become less supportive of gun control. So the correlation between GPA and support of gun control is not the same for these two groups of students. So that means there's moderation going on here, and the moderator is major. Okay? Major is the moderator. It can take two values in this case. One value is COMG, the other value is psychology. Okay? So that's what the answer to this exercise. Lastly, a very important point I would like to make before it's too late. So if we return to the formidability hypothesis once again, it turns out there's good evidence that there is a positive correlation between physical strength and proneness to anger, such that stronger individuals are indeed more easily angered. So, a positive correlation between strength and anger. Another way to say it is that the values of two variables change in the same direction. Anger and strength, they positively co-vary, right? Co means at the same time, together. Vary means change, right? Change together, right? And they do so positively. But the question is, does this covariation, does this positive correlation mean that strength will cause anger? So this is what I mean by the title of this slide, that is correlation and causation. Are they the same? Can we claim that strength causes anger because we observe a positive correlation between these two variables? Well, the answer is no, right? Because bear in mind, correlation does not imply causation. Causation is a very special word in science. It's so special that there needs to be lots of evidence from very well controlled studies before we can make any claims about causality. It is, in fact, so difficult to establish causality that researchers are usually very, very cautious in drawing conclusions. So, in this sense, causation is a very sacred word in science, right? So, logically, there are several criteria that needs to be made or met before we can claim that A caused B. So the first criterion is that, if we assume that A is the presumed cause, B is the presumed effect, right? We want A to be the cause, and we want B to be the effect. Well, in order to claim that A caused B, we first of all must establish that A correlates with B. So correlation is different from causation. That does not mean that these two are totally unrelated. Instead, correlation and causation are closely related in such a way that the first criterion to establish causality is to establish that there is a correlation. Positive, negative, doesn't matter, between the presumed cause and the presumed effect. Without correlation, in other words, there's no need to discuss any further, right? This is a necessary condition. Correlation is a necessary condition for causality to happen. The second criterion is that beyond the correlation between A and B, A, the cause, must happen before B. That makes sense because cause effect, cause effect, cause must temporally occur before the occurrence of effect. It can be the other way around, right? It can be, otherwise B will be the cause and A will be the effect, right? So you must establish A happens in time before B. The third criterion is there's no alternative explanation of the correlation between A and B. That is, in the terminology that we just learned, we must rule out all possible confounding variables. The correlation between A and B must be real. It can be spurious. Okay? In other words, to sort of summarize all three criteria, right? if A is present, then the result, it will be the presence of B. But at the same time, if A is absent, that will cause the absence of B. So when these two criteria are met, which are equivalent to these three criteria, then we can claim that A causes B. So you see, right, there's much more to do in addition to establishing the correlation between A and B in order to establish the causality between A and B. So that's why we must be very, very cautious and careful before make any causal claims between any two variables. Just remember, causality is a sacred term in science that must be the burden of proof will be on the researchers to claim causal relationships. Okay, so on this note, we sort of finished with our lectures on concept, construct, and variables. So now we have a very basic understanding of the building blocks of science, that is concept, construct, and variables. And next week, we'll start to talk about how we can measure variables. Okay, so I will upload the slides very soon, and I will see you next week. Have a good one.